back from spring break. And so we had our midterm this week, but I haven't finished grading, so we will keep pushing our teachings on Fourier series and the Fourier transform for now. And hopefully we'll finish grading over weekend, and we'll probably have like a small midterm recap next Tuesday. But for now, let's finish chapter 3, and hopefully you can get to chapter 4, because we are a little behind schedule, but we'll see. We'll probably skip we'll try to cut chapter 4 a little down. But for now, let's finish in chapter 3, and as a quick reminder of, hopefully you haven't forgot over the spring break, so we were talking about this discrete time Fourier transform. And here are the two most important equations you will use. So synthesis equation and analysis equation, just like in continuous time. So it's Fourier series, not Fourier transform. So for discrete time Fourier transform, we are once again want to write our periodic function as a linear combination. So this is some AK of complex exponentials. So it is e to the jk omega not n. But unlike continuous time, the frequency in discrete time only makes sense between 0 and pi, and when you factor in all this omega stuff, you find out that there are only n ak that's meaningful. Okay. So this ak you only need to sum over n big N consecutive numbers, and this big N is the period of your x of n. And so you see those two equations is very symmetric. And in the analysis equation, you have ak equal to 1 over n, and sum over n for n is also over one period, your x of n, and multiply with this e to the minus jk omega naught n. Okay. And something that I said will be important is that you need to, and this is the basis of a lot of our Fourier transform formulas. So we have the orthogonality of complex exponentials. So this equation can be single of as the inner product for two complex exponentials, for two harmonic complex exponentials. Okay. So for the discrete time, it's easier to see this as an inner product, because you can think about discrete time signal or period n, so there are n values. So you can think that as an n-dimensional vector, right? And when you take the inner product of those two n-dimensional vectors, that will be this form. And anyway, so if you have a harmonic with e to the jk omega naught n and a harmonic with e to the jr omega naught n, and you take the inner product, and you see that they are zero unless k minus r is the integer multiple. And we have those this intuitive picture way to see this, because if j not equal to r, if k not equal to r, then you are summing over like equipartition points on a circle in a complex plane. And because they are equipartitioned, so you will sum over, you will go to the origin, which is 0. And there is a similar thing in continuous time, although you can no longer quite see this as a finite dimensional vector. But anyway, so you take two functions and you multiply them together and take the integral. You can think of this as also an inner product. And the thing is, this is also 0 unless k equal to n. And that you can just visualize this integral as you are integrating some complex exponential, and this complex exponential its real part and imaginary part will oscillate up and down, and you're integrating over one period, that'll just be 0. But when k equal to n, you are integrating over the constant function of 1, so you'll get something. So this is orthogonality, and is using those you can get the analysis equations. So analysis equation, you are thinking you are getting a coefficient by taking an inner product of your function with one of those orthogonal bases. Okay. And there are some normalization, this one, etc. Anyway, so this is a discrete time Fourier series, and it's different from continuous time in that this is also always converge. Those two things always converge. So this is the exact transformation between x of n and a of k. So there are big N x of n to describe your function, and there are big N different ak to describe your Fourier coefficients. So the number of variables are the same, and so both of them will contain the full information of your function, and when you transform back and forth between them, there is no convergence issue. This is always exact. So there is no convergence issue, there is no Gibbs phenomena. Okay. So that's a quick review of discrete time Fourier transform. Any question so far? No. Okay, then let's go to the next part. So the property of discrete time periodic signal. So or more like the property of the discrete time Fourier series. Oh, sorry, keep mixing series, Fourier series and Fourier transform. But anyway, so we are talking about discrete Fourier series, and these were properties, and they are very similar to the continuous time case. So the continuous time case is something that we included in the midterm. And anyway, so this is a quick and easy result. So here is a listing of all the properties just like before. So we had a pi table 3.1 for the continuous time. Now we have this table 3.2 for discrete time. So you can see them here. And let's not go over them one by one because they are very similar to a continuous time, and we just have a few of them that are a bit different. So multiplication, although the idea are still pretty similar. So multiplication, you have that if you multiply your x of n, your signal x of n and y of n. So once again, multiplication on one side, you have convolution on the other side. So you have the corresponding series coefficient will be the convolution between ak and bk. But the convolution is a little different because now ak is a periodic function and bk is a periodic function. So you need to take a periodic convolution, meaning that the summation over L only summing over one period. And for the detail of the proof, you can check out the problem. But it shouldn't be too hard. And then there is first difference equation, and this is corresponding to the differential equation because in discrete time there is no differentiation. Okay, so instead we have first difference. But you can see this is kind of boring because difference, then this is just combining linearity with time shift. So you shift this -1, you get this extra e to a minus jk omega naught. And then you take a difference, then by linearity you just take a difference here. Okay? And then there is also a possible relation. I believe the normalization is also a little different, but the high level idea is the same. So the high level idea is that the energy in the time domain equal to the energy in the frequency domain, and you are summing over one period, but because of normalization we choose. So normalization, so different books will have a different convention, but for the convention in our Fourier series equation, we'll get this 1 over n here. And once again, you want to see the detail, you can check out the problem. Okay, question? No, okay. Then let's see some example of how this works out. And well, this is also similar to the continuous time thing we do. So we want to find the Fourier series coefficient for a signal looking at this. So it's easy to see that it's something with periodic period phi. And so you have 1, 2, 3, 4, 5. And it's keep repeating, and 2 of them have height 1, and 3 of them have height 2. Okay. So this is our periodic signal with period phi. And we want to use some of the property we learned to find this Fourier series coefficient. Because obviously you can brute force with your, once again, wait, never mind. Yeah, you can brute force your analysis equation, like summing over one period to find it, but we want to do it a little smarter. So we break it into two signals. So one signal is we cut off all the 1 here, so we get the x2, that's just a constant 1. And then we are left with, so if you subtract 1 from here, you're left with 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. And okay, so this is x1. And this x1, we actually already seen this is a square wave. Hopefully you still remember. It's not quite square, but it looks a lot like square wave, right? This is a discrete square wave. So you have the square part and the 0 part, square part and 0 part. Yeah. And okay, so we have our Fourier series coefficient for the original signal is AK. And then it's breaking into x1 with its coefficients bk and the x2 with coefficients ck. And the bk we say we already seen it, so here we write down we have a small review of what we have done before, what our calculation shown before. So we've done a summation for bk already because we've seen it already. And here's the result is something sine something over something with this different n1 and n. And here we can pick the n1 and n. So n, big N will be the period, and we say the period is 5. And this n1 is, so before it's like the half width here, so n1 is 1 because there's 3 things here. Okay. And anyway, we plug in these results, so we get bk is this thing. Well, and this is for the non-zero k, and for k equals 0, because it will be sine 0 over 0, we need to take down spatial treating. So you will take the average. You will take the, but for the 0 term, we know it's the DC term is just the averaging over of the signal over one period. So it's 3 over 5 things. So it's 3 over 5. And it's also nice because if you take the sine over sine with the limit of k go to 0, then that's also 3 pi k over 5 divided by pi k over 5, that's also 3. So that's nice, but if you want to be careful, then you need to calculate this separately. And so that's for bk. And for ck is easy because you see there is no variation here, so there is only DC term. Okay. So there is only the constant term with k equals 0. So the constant term is obviously 1 because it's all 1, so the average is 1. And there is no other term because it's a constant. Okay. So yeah, so very easy. You can get AK, just add those two up. So for k0 equals 0, it's the sine over sine, and k equal to 0, then it's this 1 plus 3 over 5, 8 over 5. Okay, pretty easy example. Question? Not? Then let's see other kind of question. So this is like a detective work, and yeah. You should see this in like later part of your test, or you should also see this in homework. And anyway, this is quite, I find this quite interesting. So this is detective work for you to piece in together all that I can. So those kind of question will have you try to figure out the coefficients of some periodic function. So see how it works out here. So it says you have a periodic function with period n equals 6. So it's nice arterial period. And then we have those weird conditions. So first is you summing over, and from 0 to 5, xn equal to 2. And 0 to 5 is also is one period. So 0 to 5. And the second one we have somewhere n from 2 to 7, and the -1 to the n times ux of n equal to 1. And but here we see that it's a periodic function, so as long as you are summing over 6 different values, 6 consecutive values, So this 2 to 7 and 0 to 5 basically saying you are summing over one period. And let's see. We are asking, we have a condition that x of n is the minimal power per period among everything that satisfies those two conditions. Sorry, those three conditions. Okay, and okay, so we didn't say, but the question is you want to determine what's x of n. Okay, and as I said before, those kinds of quadrant you solve by trying to piece together all the AK fitting all the conditions. Okay, and yeah, we are writing this in nice order. So it's easy to solve this one by one. Okay, so let's see. So the first one says that big N equal to 6. So we have 6 different AK. So A0 to A5 or A1 to A6. And then we need to think a little harder about the other conditions. So how do they actually tell us about our AK? So this condition is actually, so we see our synthesis equation and analysis equation, and you see this is very like this, and but actually this is just basically doing the average, right? You are summing over your x of n over one period, then this easily determines the average of your signal. And you know the average of your signal is just your A0. Okay. And you can also see from here. So if you take k equal to 0, then AK is 1 over n, sum over x over n. Okay. And you have the sum over x over n determined here. That's 2. And we over know our big N, so we know our A0. So this equation will determine your A0. Okay. And I guess okay, important thing here is also that those equations for different AK are independent. So this only tells you A0 and it doesn't restrict all other because every AK is independent. So this is the equation on A0 and you are still free to pick all other A. Okay. And okay, so similar to 2, so the 3 will also told you something. Will also told you some. Excuse me, some AK. And which K is it? So this is -1 to the n, and we want to fit it here. So we want e to the jk omega naught n equal to -1, and well, that will happen at k equal to 3 because your n equal to 6. Okay, and yeah, so you want your k omega naught equal to pi, right? Because we know -1 equal to e to the minus j pi, right? So if you have a minus j pi here, then that's -1, and this n will become this -1 to the n. So you want k omega naught equal to pi, and but your big N is 6, so you want your k to be half of your period, right? Because omega naught is 2 pi divided by n. So if you have k equal to half of n, then k omega naught will equal to pi. Okay. So if you have a half frequency, then this jk omega naught n will be the highest frequency you can get in discrete time is -1 to the n. Okay. And yeah, so this thing is actually correspond to A3. Well, it's A3 times n, and so you divide by n, you get A3 is 1 over 6. And once again, this equation is independent of all other equations for. Yeah. So this determines A3 and it doesn't affect any other AK. So we are still to pick all other AK. And we'll pick all other AK as this property. So this property says that we want minimal power. And by the possible equation, we have that the power in Xn is proportional to power in AK. So there is a difference in think. Okay, so anyway. Oh, okay. So this is the power per period. Okay. So power per period for the Parseval relation, we'll get is actually equal to this. I guess the energy in one period. So this is not quite power. This is power times the period in the frequency domain. And anyway, power will equal to the sum of AKs squares. And so we want to minimize this. And A0 and A3 are already fixed. And those are all positive numbers. So the smallest possible way to pick those are for the all undetermined ones. So this A1, A2, A4, and A5, we pick them all 0. That will minimize this summation. Okay. Any question on this kind of question? So, yeah. This is this is a little non-standard in that when you are given, so in the middle we'll give some weird conditions, and different problems have different conditions, and you need to be familiar with the properties of the Fourier coefficients to see that how they actually say about your coefficients. Okay. This is an easier example because those two conditions directly correspond to the some success equations, but sometimes maybe I will say xn is a real function, then that means that say maybe I say it's a real even function, and you will see that means some of your ak is related to some other ak in some way, right? So because say for example if xn is real, then it means a1 will equal to the complex conjugate of a minus 1, etc. Okay? So you need to be familiar with the properties to solve these questions. And anyway, so we say we want to determine x over n, so actually there are a little bit more to do on this question. So we get all the ak, so we get this a0 to a5, but we want xn, so we need to use this synthesis equation to get your xn from your ak. But let's just plug in a formula. So we have a0 here, a3 here, or a here, and your xn will be a0 times a0 is a constant term, so it's just a0 here, and a3 with the a3 is being the highest frequency term times e to the j pi over n. So it's 1 over 3 plus 1 over 6 times this minus 1 to the n, and we are plotting it here. It's period 6. Okay, any question? If not, then we are finishing. We have finished the Fourier series. Okay, and so those are about the Fourier series decomposition of the of the periodic signals. And now we go back to the starting of the chapter. Remember we said that we want to decompose our periodic signals into Fourier series because in the end we want to solve a TI system. Okay, so finally we are back to analyzing systems. And this is our excuse at the start. We said that those complex exponentials are the eigenfunctions for a TI system with those eigenvalue big H of S, big H of Z. Okay. So this is a reminder of the starting point. Okay. So the input will CI and get output, and so for continuous time, this exponential function e to st will be eigenfunction, and so the output will be the same e to st with some eigenvalue h of s, and for the discrete time it's basically the same, but we like to write e to st as z to n, and the output will be h of z. This is the eigenvalue depending on z, and times the same z to n. And we have seen that we can get those big H from small h with those two equations. So there were derivations. So want to see it, you can check it. And the small h are the impulse response, and we've seen that a lot in the midterm and chapter 1, chapter 2, mostly chapter 2. And this big H are called system functions. Okay. So we've seen how to calculate big H from small h, and in I believe next chapter we'll see how to calculate small h from big H. But for now we see that they are related. Those are impulse response and system functions, and both of them totally describe your LTI system. Okay. And so then now there is something extra. Those up to here are what we have talked about at the start of the chapter. But now we want to say we restrict our S. So before the S was any complex number, but now we want to restrict S to purely imaginary, or Z to purely imaginary exponential, the e to the j omega. Yeah. And I guess this is justified by the thing we've been doing, right? We've been saying that we want to analyze in periodic functions, and we find out that for all the not too bad periodic functions, so for those that satisfy the Dirichlet conditions, we write them in Fourier series. Okay? And Fourier series are complex exponentials, and more importantly, Fourier series are complex exponential with purely imaginary coefficients, right? So when we write periodic functions in Fourier series, in those complex exponential Fourier series, we found out that we only need to describe them with this purely imaginary s, is e to the j omega t. Okay. And so even if we focus S on just purely imaginary, we are able to describe all the periodic function and with their Fourier series, is the Fourier series synthesis. Okay, so those are very nice, and we focus on those, then basically nothing changed. But here we introduce some notation. So we say that we want to think about input being some complex exponential e to the j omega t, then we'll get excuse me. Then we'll get some h of j omega. So we are basically just substituting s to some purely imaginary number h of j omega. And similarly for discrete time, although we have we have z here, so it's actually e to the j omega. Okay. And when we restrict h to h of j omega, h e to the j omega, then those are called frequency responses, because omega, as we're seeing, can be seen as the frequency of some component of your signal, right? Because so this e to the j omega, you can think about is a complex exponential, or like a sinusoidal oscillating with frequency omega. So so if you restrict your S to pure imaginary, then you can think about it's a response of your system to signal with some frequency omega. This is basically your response it's basically the response of your system to e to the j omega t, right? Okay. So it's a response to the frequency omega. And similarly for discrete time, although discrete time, just because of notation, is e to the j omega instead of j omega. Okay. Question so far? We haven't actually derived anything, we just do some notation here. Okay. And anyway, so now we kind of focus on this h of j omega, and then we repeat the thing we kind of did before, but with the Fourier series representation that we learned. Okay. So we say that if we have some periodic signal x of t, and And we learned that we can write it in a Fourier series representation. It's some k from minus infinity, aka to a j k omega t. See those complex exponentials. And then if it's sum as a linear combination of complex exponential, then we see that we can calculate its output to some LTI system with, okay, so I should say LTI here. LTI. Although it's kind of obvious because we say system function. If it's not LTI, we will not be saying system function. Okay. So if we put x through a LTI system, and if we know the system function h, then we can write down the y of t directly. This we also already do. I'll just see that we can do this for any periodic signal, because every periodic signal we can write in Fourier series representation. And then the output will be just every e to the jk omega naught t get the corresponding eigenvalue e to the jk omega naught. Okay, because x equal to the jk omega, x equal to jk omega naught here. Okay, so this is easy. And let's see a more concrete example. So we have our x over t is something we said before in example 3.2, and let's write it here. It's something already in this Fourier series form, and we have all the coefficient lists here. And yeah, so it has something with omega naught equal to 2 pi. So I believe that means, yeah, so that means t equal to 1, big T equal to 1. And anyway, so it goes through a LTI system with this kind of impulse response. So the small h of t is e to the minus t, so some exponential decay and cut off with u of t at t equals 0, like this. And okay, so here we need to do a little bit of calculation, because here we want this big H, and we are given small h of t here, so we need to calculate the big H of j omega through small h of t by doing the integration in a few slides before. So integration here. Okay. H of j omega equal to this integration t from minus infinity to plus infinity h of small h of t to minus j omega t dt. Okay, so let's do that. And here we actually use tau instead of t because the remainder is something we will integrate over. Okay, and instead of minus infinity, we go 0 because we are cut off with this u of t here. Okay, so and then we are left with e to the minus t still here, so e to the minus tau, and e to the minus j omega naught tau. That's just something you need to do when you change from small h to big H. And you do the integration, you get 1 over 1 plus j omega. Okay, and okay, so some small tricking. So all the t or tau should disappear because you integrate over, and this is a function of omega, or more like a function of j omega. And this is a function of j omega. That's very nice. 1 over 1 plus j omega. Okay. Okay, and then we can write down our y of t now. Okay. And so yeah, y of t will be sum over the same range of k, so k from minus 3 to plus 3, because the x of t has k from minus 3 to plus 3, and some bk e to the jk omega. So we hide our big H in the bk. So bk will be ak times 0h. And so if you plug in the number, then you will get numbers. So bk, you see, bk, and obviously, so this h will also depend on k, because for different k, we'll get different omega. So you see the omega equal to k times 2 pi. Okay? Because, yeah, omega equal to k omega naught, and omega naught equal to 2 pi here. And yeah, so you plug in a number, you see those bk. We are returning a very separated form, so those are aka times h part, because h part looks a bit ugly. It's 1 over 1 plus j omega. Okay. And you see for different k, you get different omega. Okay. is 2 omega 2 pi, 4 pi, 6 pi, minus 2 pi, minus 4 pi, minus 6 pi. Okay? Question? About getting the output of LTI system by calculating the system function. Yeah. Then, okay, that's that. Oh, okay. So something to say here, and so yeah, so I think that every LTI system you seem to be able to do that, but it's not quite true. So you want to do this, then you need to be able to calculate your h of j omega. So there are also some convergence issue. So basically, when you do this integral, you need to integrate to a finite value, right? But that's not always true if your h of t is something bad. Say if you have 1 here, then this integration doesn't converge, then you don't get the finite h of j omega. So that's bad. And later we'll see that you want this to happen, then then your LTI system need to be stable, meaning that your absolute value of h of t integration should be less than infinity. Okay. And here we are talking about continuous time system, and similarly you have those things for discrete time system. Okay. So that's something to note. Okay. Any question about using this Fourier series case decomposition to calculate output of LTI system? I think it's pretty straightforward. As long as you get big H, then you just multiply all the coefficients with big H. Okay. So now we basically have a different way to see our LTI system, right? You see that our LTI system can be totally described by this big H, and what this big H doing is it multiply every frequency component with your big H, right? So then we can get into the idea of filtering, because depending on different big H, you can, how do I say? So basically we are kind of classifying our LTI system by what the big H is doing to different frequency. So every LTI system is described by this big H. Well, at least if we only consider the response to periodic signals. So they have this big H responding to different frequencies, and yeah. So if they have a particular shape on this frequency response, then we'll give them different names. So maybe let's see some examples. So like we have frequency shaping filters. So it's something that changes the shape of spectrum. So basically everything. So maybe see some example. So let's say we have this differentiation, and so your LTI system is differentiation, and that means your output y of t equal to dx dt. Then then you can calculate h of j omega by just plugging x with e to the j omega, right? We are just using h of j omega is the eigenvalue to e to the j omega, and you plug in the differentiation, you see y of t equal to j omega e to the j omega t. And okay, so this h of j omega is just j omega, and you see that this thing, if you take the absolute value, then it has this funny shape. So yeah, so when omega equals 0, so your big H has amplitude 0. So at a very low frequency, this will just get multiplied by something very small and it will disappear. But if your frequency get higher and higher, your big H will get more and more, right? And the angle is funny shape. And so what does this tell me? This tells us that the differentiation function, you will pick out the high frequency component. More like you amplify the high frequency component of your signal, right? Because it gets larger and larger when your omega is larger and larger. And okay, so although we are talking about periodic signal, but we'll see very soon that this kind of thing also makes sense in non-periodic signal. Anyway, so this is what happens when you take the differentiation on some signal. Although we were talking about 1D and 2D, but it's very similar. Okay. So this is what this will do is it will pick out the H, because you are picking up the high frequency component, and the edges of your picture is changing very fast, and that corresponds to a high frequency component, or you can see this in the time domain directly. So the edges has a large change, so the differentiation is large. Okay. So this is an interesting filter. We'll pick out the high frequency component, or we'll pick out the edge. Okay. Okay. And another example of a system is, so this is the reverse of the differentiation. So it's taking average. So if you have a system that's just averaging over your system in 2 steps, and then you can do all the calculation, and you see that your big H will be equal to this, e to the minus j omega over 2 cosine omega over 2. And well, this is a discrete case, so we only need, remember in discrete time the frequency only has a meaningful the frequency response is always periodic with period 2 pi, so we need to take a 2 pi interval. So here we are taking the interval minus pi to pi, and we see that your frequency response is largest when you have this log frequency around 0, and it's go to 0 when you have frequency go to this high frequency domain at pi or minus pi. And this coincide with our expectation for averaging, because averaging is like the reverse of taking differentiation. So if you take averaging of a signal, you should smooth out all the rough edges, because you are averaging the quick changing part. And in a frequency domain, that means that you are getting rid of all the high frequency component and picking out the low frequency components. Okay. Okay. So those are two things, and so those are the averaging system and the edge picking system. I believe in the part we skipped of chapter 2, there is also a little more discussion on those two things. But this is what they are doing. So if you take a differentiation, we'll pick out the edge, and you take an averaging, then it will smooth out the signal. And here we also have this frequency domain discussion. And anyway, so if you are engineering minded, then there are something a little more interesting to do. Or I guess something that more formalized. So there are also these frequency selective filters idea. So you see that sometimes we just want to pick out different frequency. As we see that we have the averaging and edge filters, they are pretty nice to process your signals. And anyway, so frequency selective filters are very specialized LTI system. So they have their big H that just look like blocks on your omega. Okay, so it's very restricted system with the H of j omega just equal to 1 for some period, so for some range, and 0 for other range. Okay, so those are frequency related filters, so they don't do anything. So once you notice is that there is no angle, right? So there is no complex phase. So previously those things is complex angles, but for filters they don't have any angles. All they do is they multiply by 0 or 1, depending on different frequency. Okay. So you think about how this work on, let's say, remember we have our this y of t equal to aka h e to jk omega t. If you apply this with h being a filter, then we'll just pick all the ak in the filter range, right? So when you sum the h will be 1 and you are left with ak, and the other h will be 0, then all those components disappear. Okay, so you see that the filter will pick out the ak with k omega naught in its filter range. And anyway, so here is the example of a low pass filter. So low pass filter means that you are filtering our range, let's say the lower part of omega. So your omega is between some range omega c to minus omega c. Okay, so this is a low pass filter. And so for the range of those h equal to 1, obviously it's called a passband, because all those frequency will pass through your filter and it will be left over. And all other parts are called stop band. Okay? Because, well, if your system is, if you are trying to feed your system with some omega being the stop band, and you pass through it, you multiply 0, you get nothing out. Okay, and obviously, so we have low pass filter, then we have high pass filter. So this is the reverse of low pass filter. So at a low frequency, it get filter out, and at high frequency, you can pass over. And also, you can have band pass filter that just filter out some arbitrary band that you like. Okay, so those are filters. Okay, question. And this is discrete time. So for discrete time, the frequency goes to infinity. Sorry, for this is continuous time. Continuous time frequency goes to infinity. And for discrete time, we have similar things. But once again, for discrete time, the frequency is always periodic with period 2 pi. And remember, the low frequency are around 0, 2 pi, and minus 2 pi, etc. So low pass filters will also be periodic with period 2 pi, and their pass band should be around this multiple of 2 pi. And high pass filter should pass at around this odd number of pi, so like pi minus pi or 3 pi minus 3 pi, etc. And then you can also have arbitrary band pass filter. But the band pass filter needs to be periodic with period 2 pi too. Okay, question? 2 minutes. 2 minutes is funny. Okay, so I guess we'll stop for now, and let's come back at yeah, 4:28. So come back 2 minutes later, 10 minutes later, and we'll talk about solving differential equation. And yeah.
怎么看它是
A3，基本上 这个是要跟那些 property 比较熟吧。就是这里是负1的 n 次方嘛。
对。
那这个负1的 n 次方在 discrete 是怎么说 ？highest frequency， 那就是我想想看我怎么讲。简单的讲是3等于6除以2，然后因为负1的 n 次方，怎么讲呢？或者可能还是从数字讲比较简单吧，就是3等于6除以2嘛。那如果你直接带进去的话，omega not 是2派除以6嘛。那如果 k 带3的话，它就会变成3乘以2派除以6，那就变2派除以2变成派嘛。
对。
那这个 e2 的 j 在这个中间变派的 j 派 n 的话，我能写黑板表怎样？omega not 等于2派除以6，然后如果 k 等于3的话，那 omega not 会等于 k omega not 会等于派嘛？我刚才说的。然后那我们看到是 e2 的 minus j k omega not n 会等于 e2 的e2 的 minus j 派 n，然后就会等于这些地不化e2 的 minus j 派的 n 次方。然后这个就是负1嘛，所以这样就变成负1的 n 次方这个是可是对啊，但是我们是说3丢进去就有这个结果嘛。如果你要知道这个3的话，你就要比较熟说，你也知道这个负1的 n 次方的意思就是你要倒推，然后你会知道说负1的 n 次方就会对应到你的 k 是 n 除以2的事情。其实我觉得，要怎么说？我觉得还蛮直觉的，就是怎么说？可能用 condition 看比较简，我讲刚刚说，就是说，我们想的是，因为它对应到的，我想想要怎么画，太多了，这样子。这个直觉是1、2、3、4、5、6号，这样。我们想的事情是什么？我们想的是我们有个 complex dimension， 那我们换 complex dimension 换 psi 嘛。所以说我们，不同的 k 是不同的 psi 在这里嘛，对不对？那如果 k 等于1的话，那我们有这个 n 等于6的事情嘛。k 等于1的话，它会是大概这样的一个psi这样子嘛，对吧？那我们说我们的方选会去点在这里，这样，对。然后 k 越大，这个越来越大嘛，然后 k 等于2的时候，会是我们这个3要变2倍这样之类的。对吧？那我们这负1的 n 次方对应到的东西是这个东西嘛？其就是下一个 k 等于3，但是我们反过来推，负1的 n 次方是我们说这个是 在 discrete 是它是频率最大的东西，它是上下的东西，对吧？上下的东西，它是一个这样的方式。插了一个那个，我这样看，那我自己有点乱掉。因为我应该要画 cos 不是画 sin。有点讨厌，好吧，不管。但是怎么说呢？然后这个东西，那我们可以看说，我这样讲比较简单。所以这个东西，这个 signal 它的 period 会是多少？我你们讲，这个-1的 n次方它的 period， 它的 b 跟好吧，这样有点乱。对，但是它 period 是 n 嘛，这里的 n k 等于2这样子，对吧？然后，但我们知道，所以它这个harmonic component 的它的 period 是 n， 但是我们知道这个整共的 period 是6嘛，对吧？那我们知道，像这个 k 等于1的时候，代表说在这里面有一个 period， 然后 k 等于2的时候是在这里面有2个 period 嘛。那这个2个 period 跟6个 period 的除下来的话，那我们可以知道6除以2就等于3这样，对吧？所以这样的话就是等于 k 这样。Okay, I think it's time to start. Okay, so back to our differential equation. Okay, and so by our analysis of our LTI system with the system function big H, or frequency response j omega, h of j omega, we can actually finish what we started on, I believe, chapter 2. So in chapter 2, we talk about differential equations with this initial race condition is LTI system and causal. And but we didn't talk about how to solve them. Here we can solve them because we know those LTI systems can be described by system functions. So we have this very funny way to solve LTI system. Solve differential system by just saying, what's this big H of j omega? Okay. So yeah. So we want to know what is big H of j omega. Then we just assume input is e to a j omega, and the output is h of e to a j omega. E to a j omega t. And the output is big H of j omega e to j omega t. And we know this is a LTI system, so we must have this kind of input-output pair, because any LTI system, e to j omega t will be an eigenfunction of the LTI system. That's very nice. Okay. And so I believe this is the more important part of this this section is how you solve all the constant coefficient linear differential equation. Anyway, here we are motivating this as we are trying to see RC see how to construct a low pass filter. And this thing you are probably more interested if you are double E, but we can look at them here also. So anyway, hopefully you remember your freshman physics. So we have this RC system, so we have some voltage and resistance and a capacitor, and you can write all the voltage equation. So we think this voltage here is a source, so you have some voltage Vs here, and then the voltage here should equal to the voltage of the R part plus the voltage of the capacitor part. And for now, if we think the capacitor part is the output of a system, so voltage here is the output, and we skip all the physics. Yeah. And okay, yeah. Anyway, let's believe the physics is correct, and you write down all the equations doing the current, etc., and we find out that the voltage should satisfy this equation. But what is important here for us is that so this Vc is the output, Vc is the input, and this is in the form of the constant coefficient differential equation, because you have constant coefficient linear differential equation. So because you have a linear in Vc here and a linear in Vs here, and the coefficient of Rc here should be constant in time. Okay? So this is differential equation we talked about before, and as we said, now we can solve those differential equations. But just say the input should be e to the j omega t, and the output should be also e to the j omega t times some h, and we plug in. Then we see that this is indeed solvable, because when you do the differentiation on e to the j omega t, so you also get back j omega t, but with extra j omega. And here nice thing happens, so everything has e to the j omega here. E to the j omega t, e to the j omega t, e to the j omega t. And e to the j omega t should be not zero, so you cancel all of them. And then next thing is then you are left with no t anymore, okay? Then you are just left with equation with omega and h of j omega. And you can move things around. Oh, sorry, so here we didn't actually do a cancel first, but we can do a cancel. Anyway, so we move things around, and we find out that h of j omega is this 1 over 1 plus rc j omega. And as we claimed before, we know this big h of j omega, we basically know our system. So, yeah. It's a little tricky because we only know h for imaginary s. But we will talk about complex h for complex s at the end of the semester. But for now, let's be happy with we know the frequency response. Okay, we know the frequency response. We already know a lot of things. Say we know how the system responds to periodic function just from what we know in this chapter. Okay? And in next chapter, we see that from this h of j omega, we also know response to a lot more functions, okay? Even non-periodic function. But anyway, so this is h of j omega. H of j omega like this. And we don't quite know how to get back h of t from h of j omega yet. But for now, this h of j omega, I believe we already seen. This is actually in the form of this 1 over 1 plus something times j omega. So this is a thing we already integrate today. This is exponential times u of t. We probably didn't. Okay, we didn't have the RC here, but it's very similar. Okay. So actually, so we don't know how to do the inverse in general yet, but we're already seeing what h of t gives this, what small h gives this big H. So let's just write down the answer. Okay, so this small h will give this big H. And anyway, we plot everything here. So our big H is a complex function. And C is absolute value. So once again, the motivation here is we want a RC low-pass filter. So you see it's not quite ideal. So you see it's picking all the low-pass component a little bit here, but it also has this weird face that we don't quite want. Anyway, let's ignore that for now. And but you also see that this is not a clear cut like ideal filter, right? So ideal filter you want like a block here. So you probably want like from 1 over RC to -1 over RC to +1 over RC, but you want a square wave. But square wave is quite hard to get. And here we are settling with this peak shape around low frequency. So it looks like a low frequency filter. And but it also has this impulse response, as we say, it's exponential decay. And the decay time tau here is RC, so it's inverse of this 1 over RC here. Okay. And we also plot a step response here. You can do the integration here and you get a step response. And so one thing I want to say here is there's some trade-off in designing your low-pass filter here. You can see in those time domain response function. So as we said, tau is inverse of this 1 over RC. So if you want a more sharp filter, so if you want this 1 over RC smaller and get a sharper filter, then the response time here will get longer. Okay. We'll say this is a step response. You input your function with the same function, and it will take a long time to reach equilibrium. And so we see that if your system is, if you are filtering narrowing range, then the response time will get longer, and your filter will take longer to reach equilibrium. Okay, so there's a trade-off here. And but as we said, I believe the more important thing here is now we know how to solve those differential equations with initial rates. And this is a summary of what we do. So we just assume our input x is e to the j omega t, output y is big H of some to being some function of j omega times e to the j omega t. And you plug in the differential equation, and this e to the j omega t should disappear, because when you take a differentiation of them, you still get back e to the j omega t, and with some ultra factor over j omega. And so you can cancel out all the e to the j omega, and you can solve for this h of j omega as a function of omega. And in a later chapter, we'll also see that if you don't want your big H, you want your impulse response h of t for some reason, then there are ways to calculate small h from big H also. Okay. And yeah, so this is how you solve your constant coefficient linear differential equation with the initial rates condition. Question? If not, then let's go back to filters. Okay, so we talk about low-pass filter, so now talk about high-pass filter. And the high-pass filter, you can basically do the same circuit. So still a RC circuit, but now you use the voltage around your resistance as your output. And then anyway, let's skip physics and actually also skip the calculation. So you do the same thing. You have input into e to the j omega t, output equal to. Now we call it G just because we just have H. Okay. Want to differentiate a bit from the big H. Okay. And you can solve for big G, and they look like this. So you can also see it's basically 1 minus 1 minus the previous thing times e2 1 minus the previous thing, right? Because the R plus C should equal the voltage here plus the voltage here should equal the voltage here. So the voltage here will basically just be 1 minus the voltage here. Well, if you are factoring all the e to j omega t. And anyway, you plotted it. Wait, actually, never mind. I think I'm talking not quite correct. It's not. Yeah, there is h to j omega c. 1 minus. Previous answer is. Okay. This is indeed 1 minus. Although, why does this look weird? Well, anyway. Let me check real quick. 1 minus h is. Oh, okay. Probably because of the reason. But anyway, so your G is j omega RC over 1 plus j omega RC. And we can plot its magnitude and phase here. So you see that its magnitude is kind of like a high pass filter. So for the about 1 over RC, about minus 1 over RC to 1 over RC region is get filtered out, and for high omega it will saturate to 1, so that's nice. And then it also has this HR angle thing, and it also has this response to the sharpness trade-off. So if you want to filter a sharper region, then its stable response will be slower. So those are very simple design of filter. Any question? And I believe if you want better design for filters, then you need to take some double E course. Okay, and then we also have a similar thing. I think the last part of this chapter we have a similar thing for discrete time filter. For not quite discrete time filter, for like solving discrete, so we have a difference equation. Okay. So we can also solve a difference equation with initial race condition because they are LTI system. So we do a similar thing. Excuse me. So yeah, so here are the steps. So you say your input is e to the j omega n. Output is h of e to the j omega e to the j omega n. So basically the same thing, just a different notation here because here we want to write z, so this is e to the j omega instead of just j omega. And yeah, then you can solve for big H. Okay. So for example, we have a difference equation here. Y minus a y of n minus 1 equal to x of n. And you plug in things, then you get your h over e to the j omega equal this 1 over 1 minus a e to the minus j omega. Okay. And okay. Now once again, this should be periodic with period 2 pi, and it is. So that's quite nice. But this thing is a bit funny. So this obviously depends on A, but for positive A and negative A, it has quite different shape. Okay. So here we have positive A, and we see that for positive A, your H, absolute value of H will concentrate around this omega around 0 or 2 pi part. So this is like a low pass filter. And for negative A, then your absolute value of H will concentrate around this plus minus pi, this high pass filter. And it's always with period 2 pi because it's e to the j omega, big omega to omega plus 2 pi is the same. Okay, so check out, and it's nice. So you can always solve your difference equation in this way. But there is other way, which I think is actually a little worse, but that's a way to do this. So if your difference equation is very nice, so it's actually non-recursive. So basically you can read out your y directly. So y equal to this, say, y equal to summation x of minus k bk from some k range. Then if the y is this simple, then you can solve this in a probably worse way. But so you can solve for your impulse response directly. So you plug in your delta function here, you get some impulse response. And then small h, then you can calculate your big H from your small h. Okay. So we'll get something. Okay. So that's another way to get back your big H if your system is very simple, so basically non-recursive. So basically your y over n don't get any time delay. Okay. So you can do that. And here will be some examples. So we have a case where our system is y is time is just a uniform averaging of period of like minus n to plus n steps. Okay. So the bk is just 1 over n plus 1 because there are that many bk here. Then your y is the averaging, and then you solve everything. You will get the h is this weird function of sine over sine. So this is a moving averaging filter. And plot this, then we find out that if you average things, then it will like the low pass filter. So you plot your h with different m and n, and you see that if you, so this n, big N will be the lower bound of your averaging, and m will be the upper bound of your averaging. And you see that when your n and m get larger, then this is getting narrower and narrower averaging, narrower and narrower, and it looks like a low pass filter. And I think ideally this also makes sense because, as we say, it's like a continuous time averaging we talked about before, right? So if you're averaging over your signal, you will average out all the high frequency recalling in your signal, and so we will left with low frequency signal. So like averaging, this is a very small averaging we talked about before. So this has n equal to 1, m equal to 0, and the idea is that you average over a signal, then you will average out all the noise, and but for low frequency components, so the thing that changes slower, that will not get averaged out, and it will be still stay, and so your system effectively become a low pass filter. Okay. And anyway, so that's for chapter 3. Any question, or we'll start talking about Fourier transform? Okay. No? Okay. Yeah. I guess small summary again. So once again, we talk about how to solve differential equation with initial race condition, and it's actually quite easy. You plug in this e to the j omega n or e to the j omega t, and the output is h times e to the j omega t or e to the j omega n, and then you just solve for this big H, and big H will basically tell you what your system do. As you solve the big H for your system, then you get another input-output pair. Then if your input is periodic function, then you can write that in Fourier series, and you will do the thing we talked about, where you have a Fourier series expansion to your input, then your output is just bk equal to ak times h. Okay? Okay, then let's change the slide to chapter 4. to do, wait, what? Oh, and I need to do this here. PowerPoint, no. Okay. Hopefully the video is okay. It says it's streaming. Maybe the TA can check it quickly. Yeah. And anyway, for the people that are here, we can look at the slides here. That's fine. Yeah. And anyway, okay. So chapter 4, the continuous time Fourier transform. So this is a very famous Fourier transform. You probably hear about it the other part. And here we will motivate it as like a Fourier series for periodic signals. Okay, so we are going to do a pseudo derivation of Fourier transform formula from the Fourier series coefficient formulas we had from the last chapter we just finished. Okay, and so we'll kind of write. I think the idea here is we want to write a periodic signals also in terms of linear combination of complex exponentials, because as we just see, complex exponentials are very nice. They are the eigenfunctions to LTI system, and we want to write everything in terms of complex exponentials. Last chapter we only do that for periodic signal, but now we want to do that for a periodic signal too. Okay. So, those are not too important for now. So yeah, spoiler. So those are the Fourier transform before we derive them. And it's very like the Fourier series thing. So there is the forward direction and the inverse direction, although we don't call them successive and analysis anymore. But there are two equations nonetheless. So your signal is this x of t, and your Fourier transform to this, I believe we call spectrum function, or so there are many names. So sometimes it's called spectrum, and sometimes it's called just your signal in the time domain. Yeah, sorry, in the frequency domain. So, so it's big X, and there is also an inverse relation where you can get your x of t. Okay. So this is So this is actually in a different order in our Fourier series, right? So Fourier series, first we can write x of t as the in Fourier series we have x of t as a linear combination of this e to a j omega t. But because x of t is not periodic anymore, so we are not restricted to the harmonic series. So this omega here is actually be anything. Okay? So omega is from -infinity plus infinity. And there are infinite of them, so we kind of just integrating over them with some spectrum function, big X of the omega here. And so this is kind of like a synthesis equation. And then we also have this like analysis equation. So we have this big X of j omega, we can calculate it from our x of t by, well, it's from this formula. So x of t times e to minus j omega t dt, then integrating over all the t. And sometimes we will think of this. So once again, because of we have this back and forth relationship, so big X and small x has same amount of information. Yeah. And so if you know big X of j omega, then you can calculate your x of t from just doing this integral. And if you know x of t, you can calculate your big X of j omega from doing this integral. So they have the same amount of information, and they can be viewed as the same function, just in different perspective, or people would like to say in different domain. So sometimes the x of t will be called a function in the time domain, obviously because of t of time, and this big X of j omega will be called a function viewed in the signal. The signal viewed in the frequency domain, because this omega is the frequency. Yeah. So these are the Fourier transform pairs. Big X of j omega equal to but also you see now there is more symmetry. because before when we talk about continuous and Fourier series, x is a periodic function and the coefficients are discrete value, right? So in the last chapter we have ak here and the k taking values well, k has discrete values, but here the omega is not discrete value anymore. The omega is continuous thing from -infinity to +infinity, and t is always +infinity to -infinity. Well, t is also not periodic, so instead of t instead of over one period is also now from -infinity to +infinity. So that's very nice. And those two are probably the most important equation for chapter 4. And but anyway, so let's take a step back. We want to derive them. Okay. So we want to do a not very rigorous derivation of them by saying that we want to view them as you take the Fourier series transformations, and remember that's only for periodic function. Then we take the period of the periodic function, that is big T to infinity. Then we think that in the t goes to infinity limit, our analysis synthesis equation for Fourier series will become those two. Okay. 20 minutes should be enough. Okay, so I guess any question before we go to the details of the derivation? Those are two equations. Okay. So how does this work? This is kind of wavy like all the calculus stuff we do. But anyway, so hopefully this gives you some intuition. So we will start with our Fourier series representation. So we start with some periodic function that look like this, right? And we pick a very specific periodic function. So it's square wave. We have seen them quite a bit of time. So it's square with -t1 to t1, and it's a period t. So it's repeating itself. Okay, and we are thinking if we take this t to infinity, then all those repeating will get further and further away, and it will look like a periodic function, right? Because if you don't see this repeating, then it's just one square here, and it's a periodic. Anyway, this is a periodic square wave, and we have seen its Fourier series coefficient. And just write in here is ak equal to 2 sine k omega naught t1 over k omega naught t. Okay, this is just we already saw for, so let's write here. And now we do something very funny here. Okay, we define this envelope function by multiply k by this ak by big T. Okay, so basically we move this big T here. So we think about this function big T ak. So why we want to do this? Because we want to get a function that doesn't depend on this big T. Okay. Okay, and because you can kind of combine this k omega naught as omega, right? Because, well, yeah, it's k omega naught is basically the frequency for your ak, right? Okay, we didn't have it. Remember, this ak is multiplying some e to the jk omega naught t. So the k omega naught is the frequency of the complex exponential associated with your ak. Okay. So we combine this k omega naught with omega, and we kick this t here. Then the right hand side here totally doesn't depend on big T or omega naught, because omega naught will combine with k become omega. Okay? So this is now a function of omega only here. Okay? This is 2 sine omega t1 over omega. Okay? And it's called the enveloping function, the tak. And this is independent of, so this part is independent. You don't see any t or omega naught here. It's just a function of omega. So you can so we can kind of reverse thinking here. So now we have this TAK enveloping function, and this AK is actually just taking points of this enveloping function at the value of omega equal to k omega naught, right? So this 2 sine omega over omega sine omega t1 over omega is the envelope, and your TAK, you are just taking samples from your 2 sine omega 1 over omega. So maybe it's easier to see this as in pictures. So here we plot this envelope 2 sine omega t1 over omega here. So if we don't change t1, it's fixed in here. So and and we see that if we pick so we have some t. So if we fix some t, then we will have some spacing over your sample. Okay. So so we have a different t here, right? So we have t equal to 4t1. So remember, t is the period here, and the t1 is the spacing of a square here. And we are thinking about we are picking the t larger and larger. Okay, p larger and larger. Okay, so where t is and omega is sampled at k omega naught, and the omega naught is 2 pi over t. Okay, so if t larger, then your omega naught will get smaller. Then you will sample at more points. So here we have a different t. So t equal to 4t1. Then we'll sample. Then then those k omega naught point will be kind of spaced out here. And then we have a bigger t, so with t we double it, p become at1. Then your omega naught will get halved. So you see those k omega naught are more dense points on those enveloping function. And then we have even higher t, so we double t again, t to 16 t1. Then we have even higher points, and the sampling k omega naught will be even higher points. Yeah. So we see that if we get our t bigger and bigger, then these omega naught points are getting tighter and tighter. And we are thinking our AK are so those TAK, or TAK is basically AK but multiplying T. Those TAK are going to get more and more simple point on those enveloping function. But I guess once again, a very important thing here is to note here is that this enveloping function doesn't change when you change T. So we are just staying the same enveloping function. And just as we said, so as t increase, the omega naught will decrease, and you are sampling more and more, more and more on this enveloping function. And yeah, and as t goes to infinity, then we are basically taking every point over the enveloping function. So why don't we just take this envelope function as basically our coefficients? Okay. That's what basically what we'll do. So this enveloping function will become the spectrum of your periodic signal. And so basically the enveloping function we'll see it will become this big X of t. Sorry, big X of j omega. Okay. And we'll talk about, it will keep a record of all the frequency component of your periodic signal. Okay. Okay. And yeah, as we said, so we take t goes to infinity, then because the repeating is happen less and less frequently, your signal look like a periodic signal. And the enveloping function, because it doesn't change with t, will give you all the information about all the very dense sampling of your frequent Fourier series coefficients, and eventually become the spectrum of your Fourier transform. Okay. And let's do the derivation a little more. I think it is kind of like going the other way. This is a bit circular, but it works. Okay. So before we starting with the periodic function, and we say we pick the t goes to infinity. And now we start with a periodic function. We are doing things a bit funny. So we start with a periodic function, so x of t here, and for simplicity, let's assume it has some finite support, so it has some range from -t1 to t1. And well, we start with a periodic function, but we only know how to do Fourier series coefficient for a periodic function. So we copy paste this from -infinity to +infinity, and make a periodic function. Okay. So now there are quite a bit of functions, so it takes some time to remember them. So you start with a periodic function x of t, and you repeat it for some t bigger than 2t1, and you get a periodic function x tilde of t. Okay? So from every x of t, you can get the x of tilde of t. That's pretty easy. You just keep copy paste your x of t every big T. Okay? And you need to pick a big enough xt, big T. Okay? And okay, so this is kind of circular, but what do we need to do? So get x of t to x tilde of t, then we take big T to infinity, then that will become a periodic function that looks really like x of t. Okay, so we go from x of t to x tilde of t, then we take it big T to infinity to go back to something that looks like x of t. But now that's periodic, so we can kind of analyze its Fourier coefficient, how it goes. Okay, so question about what we are going to do. A bit confusing. But anyway, okay, so that's what we'll do. Let's go see how the math work out. Okay, so x tilde of t, as we say, is a periodic function. So we can do what we know from chapter 3. The periodic functions, we write down the Fourier series formula. Okay, so x tilde of t will be sum over those harmonic complexes exponential e to the jk omega naught t, with omega naught equal to 2 pi over t, and with different k and k from -infinity to +infinity. And okay, so the question we are going to play around is this ak. We also have this analysis equation. So ak, and we say it's here. So ak is integration over one period. So let's take our period from -t over 2 to t over 2, and x tilde of t to -jk omega t dt. Okay. So nothing really happened here. We are writing all the Fourier series formula here. And okay, so but now we do something funny. So ak equal to this thing, so it's integration from some -t over 2 plus t over 2, so maybe something like this period. Okay, let's use pen here. So we are integrating something like in this period, right? One period of x tilde of t. But but you see that if you're integrating over this period, then, well, it's only one period, so there's no repeating. So integrating over this -t over 2 to +t over 2 of x tilde of t is the same as integrating over this for x of t, right? Because those two functions are the same in this -t over 2 to +t over 2 interval. Okay? So those two functions are the same in this integration interval for your ak. Okay? So you can change that to x of t. Okay? So if it's x of t, you can change to x of t. But now you are integrating over this for x of t. Okay? So we are now integrating over here. Okay? If you are integrating over this for x of t, then you can also just change the integration interval to infinity, because there is nothing outside of this integrable for x of t. Okay? And yeah, so that's what I do. So ak we can also express as this integration for x of t. So this is -infinity to +infinity x of t equal -jk omega t dt, and divided by 1 over t. Okay? So here we do some clever substitution, and this is still AK. And now we define this envelope function of t times AK again, because you kind of see that this enveloping function is very nice. And it's indeed very nice. So if we have t times x of t, once again, now this thing is independent of our big T. Because, well, you times big T, then this 1 over T disappear. Then your integration x of t e to the j, now we have k omega naught t here. But once again, we say k omega naught is just omega. Okay. So this is e to the minus j omega t dt. Okay. And yeah. And we see that now this thing is independent of big T. It's very nice. And kind of independent of omega naught, although yeah. So now it is a function of omega, and we'll think about if we have some omega naught, then we'll have k omega naught equal to omega. Okay. And okay. So we can define this envelope function big X of j omega as our TAK before, and we see that. So before we do the analysis only for square function, but now we see this x of j omega, big X of j omega being independent of big T is actually true for any function, right? Because we don't have a particular form of x of t. You just see that this works here. And okay, so now we define our big X is independent of big T. That's very nice. And then we kind of reverse here. And we divide this, then we see that AK is x divided by 1 over t, just basically the definition. And also you plug in the omega with k omega naught. Okay. So once again, you see AK is like a sampling of x, well, divided by 1 over t. And now we do something funny. Okay. So now we plug in our synthesis equation, and now we try to derive how to express. So basically, we want to express x of t as big X, because now we have the expression for big X for small x, and we want to get small x from big X. And to do that, we express small x tilde with big X, and that's by plugging the synthesis equation. So once again, synthesis equation is this, right? So synthesis equation is you can express x tilde with AK, and we kind of change AK to big X, and so we do the reversing. So we have AK equal to like big X divided by t. Then we swap this AK with big X divided by t, then we can express x tilde instead of big X, and then look at this, okay? And it's taking sample at omega equal to k omega naught, okay? And yeah, wait, isn't this? Oh, okay. And okay, so x tilde, so you plug in the equation, you look at this. And now we can do some swapping here. So don't want to see this big T. So we have this 1 over T become this omega naught divided by 2 pi. Okay? So nothing really happened here. And but actually we're almost done. So now this equation between x tilde and the big X, and it's some summation that depend on summation on k that depends on omega naught. And now we want to do is we want to say this summation actually looks like an integration when you take t go to infinity or omega naught go to 0. It's because if you look at this summation, then it's like a summation of all this part. How do I do? Okay, I forgot. So let's maybe do this. Okay, so all this part. This work, yeah. Okay. So it's like a summing. So we think those parts are like a sampling of some function x of j omega e to j omega at point k omega, right? So think about this plot. down here. Okay, so this we have this line of x of j omega equal j omega t. Although it is a little funny because it's a complex number, but let's pretend that we can plot the complex number. Okay. Okay, so we have a function x of j omega equal j omega t here, and now we think about so this summation will be like summing over area of this function with staircases with a lot of rectangles, right? Because if you think about, okay, so we have the example here. So think it will be a lot of rectangles like this with spacing being omega naught. Okay, let's draw a little more rectangles here. Oh, too high. Oh, eraser is dangerous. So let's do eraser like this. Okay. Rectangles. Yeah. So this is like what you do in calculus, where you approximate your area under your curve with summing over those rectangles. And let's see that this summation is actually summing over the rectangles. So we are saying the starting point of those rectangles are at k omega naught, and we have k from minus infinity to plus infinity. And so this omega naught will be the width of your rectangle, because you go from say like k omega naught to k plus 1 omega naught. So these widths here are always omega naught, and the height here will be this x3 omega e to j omega, taking value at omega equal to k omega naught. So the height is x of jk omega naught e to jk omega naught t. This is exactly the height of the rectangle, and this omega naught is the width of the rectangle. And so this term for 1k is the area of this rectangle at the starting point being k omega naught. And we are summing from k minus infinity to plus infinity. So this whole thing is the sum over all those rectangles from minus infinity to plus infinity. And it's an approximation to the area under this curve. And we think about as t go to infinity, this omega naught will go to 0. And the summing over of those rectangle area will become the integration of this function over the area under this curve. Okay, so as big T goes to infinity, we think this becomes the integration, and 2 pi stays 2 pi here. Okay, so okay, oh, we are a little over time, but anyway, so that basically completes the pseudo derivation here. So we have written x tilde of t as this big X of j omega, and then we just argue as big T goes to infinity, x tilde of t look like x of t, so we just say x of t is also this integration, and we have get our back and forth, and this x of j omega kind of just like from the definition, we define it as the enveloping function here, right? And we derive that as t go to infinity, then x of t can be written as this integration of x of j omega with e to j omega t. And next here, big X is called the Fourier transform or Fourier integral, the spectrum of your x of t. And two equations, one of them called the inverse, one of them called the Fourier transform. And yeah, okay, so just on time. Any question? Or we'll see you next Tuesday. Okay? Yeah, see you. Oh, and okay, and we also should have homework today.所以就把比赛当做一出吧。